Swayam Prabha. Digital India. Educated India.
So, we were discussing the wave functions for a particle in a 3-dimensional box. We saw that the simplest has no nodes, while the next possible one has one node. In this particular case, where I thought of psi 1 to 1, it has a node in the y equal to L by 2 plane, or if you had thought of psi 2 to 1, obviously what is going to happen, no, not 2 to 1, but 2 1 1. What will happen is that it would have a node which is at x is equal to L by 2, and where will that be? It will be actually a plane perpendicular to this plane, the earlier node plane, node right, nodal plane actually. Now, I do have a mathematical program which can show you all these things. If you look at this figure, the way this figure is constructed is as follows. You take the wave function for the ground state, right. As I said, it has no nodes. So, what is going to happen is that it will have its maximum value at the center, and as you go away from the center, the value of the function will go on steadily decreasing, right. At the center, let us say it has a value of 1, just to illustrate. Then what I can do is, as I go away in each direction, its value will decrease. There will be a particular point in that direction at which the value will be equal to 0.5, right. In each direction you will have a point where the value is equal to 0.5. You can join together all these points to get a surface, and that is a surface that is plotted in this figure. Okay. So, this again, if you look at the picture, it is so very clear that it resembles the lowest possible function, resembles an atomic orbital. The atomic orbital is nothing but the s orbital. Okay. I can draw pictures of other orbitals also in the same fashion. For example, if you think of one, which one should I, well, let me just plot this. It will take a little bit of time because this is not a small calculation, it is a fairly lengthy calculation, and the computer will do the calculation and show you how the plot looks like. As I told you, these things are plotted using the software Mathematica, which is extremely powerful. It is still doing the calculation. So, I have put one of the 3 quantum numbers equal to 2, the others are still equal to 1. So, obviously it is this one, right. It is this one that I have put. I can plot other things also, but suppose I said n1 is 1, n2 is, sorry, suppose I say all of them are 2, what would be the appearance? Let us see that. Or maybe what I will do is, I will say 2 of them are equal to 2 and the last one is equal to 1. So, I am actually not looking at 2 2 2, but 2 2 1. as I said, the calculation does take a little bit of time. It has to find the surface and then plot it. Okay, this is how the function looks like. If you want, I can even rotate it, but even rotation may take a little bit of time. Okay, it is taking time, so you see, I don't think I should try to do that. Let us look at the other function which I talked about, psi 2 2 2. This will have three nodal planes, and the three nodal planes will all be perpendicular to each other. So, we will look at that function. Now, this one, for example, it does resemble one of the atomic orbitals. It is actually kind of resembling dxy or something like that. I mean, if I think about it, I can tell you. It actually resembles dxy, this particular plot which is there now. Okay, while it is plotting, let us think of something else. See, here I have assumed that the box is completely symmetric, all the three sides are equal, right. So, if you are familiar with symmetry, you will say that it has octahedral symmetry or cubic. But suppose I now say, okay, I am going to distort this. I am going to distort the, you look at the figure, right. This box, I have assumed that all the sides are equal, but now suppose I say, okay, the length of the box in the z direction, okay, is increased. Let us say the length of the box in the z direction is increased a little bit. Then what will happen to your expression for energy? What we are saying is that this is our general expression, L1 is equal to L2, right, that is what we are saying, but L3 is a little bit different. So, therefore, L3 actually is slightly larger than L by an amount which I shall denote as delta L. So, this is L square, that is L square, and this is L plus delta L square. So, what will happen to the energy levels? The picture that I have drawn here is for the perfect cube, but suppose I decrease the symmetry of the system by stretching the box, then what will happen to the energy levels? Of course, you see this energy level 111 will get lowered a little bit, and then what will happen to 211, 121 and 112? You will find that these also 211 and 121 also will get lower, but by exactly the same amount. So, I can represent them here, they are lower than in this earlier figure. This is 211 and 121. But if you think of 112, actually 112 will get lowered by a larger amount, and that means you see these three states are no longer degenerate, and so as a result of lowering of symmetry, what has happened is that an energy level which was triply degenerate has split up into two energy levels. One of them is doubly degenerate and the other is singly degenerate. Now, in a similar fashion, the same kind of thing will happen with this. There what will happen is that 211 will be lowered, sorry 221 will be lowered, but 212 and 122 will be lowered even more, and therefore, they will remain degenerate. So, again the degeneracy of the original energy level is lifted, it splits up into non degenerate and doubly degenerate levels. Similarly, here too 113 would have an energy that is lower than either 311 or 131. And finally, of course, 222 is lowered, but there is only one energy, one state, and therefore, there is no splitting up. So, essentially the idea is this, you see, if you had cubic symmetry, you would have triply fold degenerate energy levels, and if you distorted the cube to form a rectangular parallelepiped, then what happens, the energy levels are actually split up to give you energy levels of lower degeneracy. Okay, now we will pass on to the next interesting problem. We will go back to a one dimensional problem, and we will now say that okay, I have a particle, it is within a box, but that box has a length equal to maybe L. Earlier we said that okay, outside the potential energy is infinitely large, but we will remove that and we will say that the potential energy outside is not infinitely large, but finite, and see what happens. Okay. So, to make things clear, let me imagine that I have a box which extends from maybe here to there. In that region the potential energy is low, while outside the potential energy is different and large, right. In fact, I will imagine it this way. Let me say outside the potential energy is 0. Just for the sake of convenience, outside I am going to say the potential energy is 0, and if I put it like that, then what will happen, if within the box the potential energy is actually negative, right, and I will say that this height is equal to V0. So, if the particle is inside the box, its energy, potential energy will be minus V0, because it is the box, within the box the potential energy is low. If so, but if it is outside, I will say okay, the potential energy everywhere is 0. And also it is convenient to say that okay, I will have my coordinate system in such a fashion that the origin is right at the middle of the box, and the box will, let me say, extend from minus a to plus a. So, that the total length of the box is now 2a, right. Why do I do that? Well, the answer is actually quite simple. I have already told you that if I choose the potential to be symmetric, then I have big advantages. I can classify my wave functions as being symmetric or antisymmetric, and I am going to use that, and that makes things extremely simple. If you make use of symmetry, then calculations become very easy. Okay. I want to use that, that is the reason why I chose the coordinate system to be in such a fashion that x is equal to 0 is this point. So, let me now define the potential energy of the system. V of x, how will you define it? If it is equal to it is equal to minus V0, right. V0 is assumed to be positive, right. So, minus V0 is negative when if x is less than minus a, mistake, minus a is less than x and x is less than plus a. That means the particle is within the box, and outside the box what will happen? I will say that the potential energy is 0. Now, before we go into the quantum mechanical description of this, imagine I have a classical particle. What will happen to a classical particle? You see, a classical particle can be just sitting within the box, then its potential energy will be minus V 0 and it is not moving. So, therefore, the total energy will be minus V 0, correct. So, the lowest possible energy for a classical particle, if it was subjected to this kind of potential, will be minus V 0. Or then maybe I can push the particle in one direction, giving it some kinetic energy, and then what will happen? It will, suppose I give it that much kinetic energy, then it will go hit there, then come back and go on oscillating within this box, and the amount of energy that I can give it can be anything. So, therefore, you see, it can, the particle can have any energy starting from the bottom, from minus V 0 onwards. If it obeyed classical mechanics, it can have any energy. But then of course, if its total energy is greater than 0, then what will happen? If you push the particle in this direction, it will go off to infinity. This is what will happen classically. So, classically speaking, you see this, the particle can have any energy from minus V 0 to plus infinity. Is that true in quantum mechanics? Is the question that we will answer. Okay. So, therefore, I will write the Schrodinger equation. In fact, I will only write the time independent Schrodinger equation, because we are looking for the stationary states of the system. And so, I will have the Hamiltonian operator containing its kinetic energy and the potential energy, and this is going to operate upon psi, which, and the answer has to be equal to E psi. Right. And as I told you, classically speaking, the energy of the particle can be anywhere between minus V 0 to plus infinity. And classically what will happen is that if the energy is, if the total energy of the particle is greater than 0, if it is greater than 0, what will happen? The particle will go away. While if it is less than 0, that means the total energy is less than 0, so therefore the total energy is negative. Then what will happen? The particle will actually go back and forth. So, it is bound within the box. Right, such a particle is going to be bound within the box. So, what we want to know is, quantum mechanically will the particle remain bound within the box. So, therefore, what I am going to do is, I am going to say that I am thinking of situations where the energy of the particle is less than 0. Right. I will first look at situations where the energy of the particle is less than 0. And then after that, I will worry about situations where the total energy of the particle is greater than 0, correct. So, let us try to write down the this differential equation in 3 different regions. Which are the regions? This is region 1, this is region 2, and that is region 3. I will first think of region 1. In region 1, what is going to happen to this differential equation? I will have minus h cross square by 2m d square upon dx square In region 1, what is region 1? Region 1 is the region where the value of x is less than minus a, and in that region what is the potential energy of the system? It is 0. So, therefore, this plus 0 operating upon psi of x is equal to the energy of the particle, energy of the particle multiplied by the wave function. But I told you that I am interested in the situation where the total energy of the particle is less than 0. Therefore, what I will do is I will adopt this notation. I will say that E is equal to minus epsilon, where why do I adopt this notation? Simply because I want epsilon to be positive, correct. So, I will denote the energy, I will write the energy of the particle as E is equal to minus epsilon, where I know that I am interested in situations where epsilon is a positive number. So, then what will happen? This is actually minus epsilon times psi. And what this effectively means is h cross square by 2m d square psi by dx square is equal to epsilon psi, where epsilon, remember, is a positive number. Or you can rearrange this and write d square psi by dx square is equal to 2m epsilon divided by h cross square psi. Epsilon is a constant because it is related to the total energy of the particle. And at this point, you see, as usual, we do not want to be writing this object again and again and again, it is very inconvenient. So, introduce something which I may refer to as kappa, such that square of kappa is equal to 2m epsilon by h cross square, right. This is equal to kappa square. So, therefore, d square psi by dx square is equal to kappa square psi. Kappa is a constant. So, second derivative of a function is equal to the function multiplied by kappa square. So, what is the solution of that equation? If you wanted to solve this, it is extremely simple. Well, there are two possible solutions. The first one is e to the power of plus kappa into x. In fact, I can put a constant. What is the well, let me not put a constant, I will do that in a few seconds. So, you have one solution which is of the form e to the power of plus kappa x, you have another solution which is of the form e to the power of minus kappa x. Okay. And you can multiply this by any constant that you like. So, maybe you can say, okay, C1 e to the power of kappa x and C2 e to the power of minus kappa x. These are possible solutions, as you can verify, very easy to verify, because if it just took the second derivative of this, you will find that that is equal to this function getting multiplied by kappa square. Or if you took the second derivative of this, you will find that that is equivalent to multiplying this function itself by kappa square. So, therefore, it satisfies that differential equation. So, you can say the most general solution will be a linear combination of these two, because you see, if you have two particular solutions, you can always add them up and the answer will always be a solution of the original equation. So, therefore, in this region, in region 1, what is the solution that we have found? C1 e to the power of kappa x plus C2 e to the power of minus kappa x is the solution. Fine. So, what will be the solution in this region? Well, there also the potential energy is 0. So, the equation is just the same. it is not any different, it is the same equation, and if the equation is just the same, what will happen? The solutions are going to be similar. So, how will you write the solution in this region? The answer is going to be, well, I will have some A1 into e to the power of minus kappa x plus A2 e to the power of rho plus kappa x, where A1 and A2 are some arbitrary constants, right. And now you have to look at the solution in region 2. So, what will happen in region 2? In region 2, this differential equation becomes minus h cross square by 2m. So, now I am thinking of region 2, t square upon dx square. What is the potential energy of the system? If the particle is in that region, then this is minus V0, psi is equal to minus epsilon psi. This is the differential equation. You can easily rearrange this equation. What is going to happen is, you are going to get h cross square by 2m d square psi by dx square plus V0 minus epsilon into psi is equal to 0. Right? I mean, you just multiply throughout by minus sign and then take this term to the left hand side, you are going to get this equation. Or if you like, you can rearrange and write this as d square psi by dx square plus 2m by h cross square V0 minus epsilon psi is equal to 0. Now, V0 is a constant, epsilon also is a constant, right. Therefore, this whole thing is a constant, and it is perhaps convenient that I introduce another constant, which I will define to be such that the new constant that I am introducing is q, and I introduce it in such a fashion that q square is equal to this number. So, therefore, in this region the differential equation has the form d square psi by dx square plus q square psi is equal to 0. That is in region 2. So, what is the solution in that region? This is like particle in a one dimensional box that we have already discussed. The solution is actually, it is possible for you to write the solution as maybe some B1 cos k, not k but qx plus some B2 sin kx. Oh, sorry. I hope you do not mind if I change notation slightly, because what comes to me naturally is k. So, what I will do is, I will say, instead of calling this q, let me just call it k. K square is defined to be equal to that. So, therefore, here you are going to get k square. And naturally, the solution will be B1 cos kx and B2 sin kx, where k square is defined to be equal to 2m by h cross square V 0 into V 0 minus E. So, these are the solutions in different regions, but it is not enough to get solutions in these different regions. You have to ensure that the solution that we are getting is acceptable. So, let us look at the solutions that I have. In this region, I have a 1 e to the power of minus kappa x plus a 2 e to the power of plus kappa x. Now, suppose I allow x to go to infinity, what will happen? This term I would expect will decrease, because it is e to the power of minus kappa x. But what about this term? This term will increase to infinity. So, if you said that this is your wave function, you are actually saying that the particle, as you go away from the box, the particle is more and more likely to be found. In fact, the probability that it will be found at a very large distance is extremely large, because this will tend to infinity as x becomes infinitely large, and that behavior is not acceptable. I mean, there is no physical reason for that to happen, and therefore, the only way in which I can get out of this difficulty is to say that a 2 must be equal to 0, otherwise I am not going to get an acceptable solution. So, therefore, straight away here I can say a 2 must be equal to 0. You think of this other part, right? Look at this part. Here imagine x is going to minus infinity. Then what will happen to these two terms? You have e to the c1 e to the power of kappa x, x is going to minus infinity. So, what will happen? This term actually will decrease to 0, while what about the other term? It will increase to infinity, and therefore, this term is going to give me problems, and therefore, to have an acceptable solution I am forced to put C2 equal to 0. So, therefore, in this region the solution has to be simply C1 e to the power of kappa x, right. The other part I have to throw out. Now, you have to be very clear as to why this is done. See, I am saying that the total energy of the particle is less than 0. So, therefore, what do I expect? I expect that the particle will be trapped within this potential well. It has no possibility of going away, right, and therefore, the probability of finding it at a large distance has to be vanishingly small, right. That is what we are doing. Now, as far as this part is concerned, what do we do with this part? Well, I have this very interesting possibility. See, I know that my solution to the Schrodinger equation for this problem, it has to be either symmetric, it has to be an even solution or an odd solution. This is what we have proved in the morning, right. So, suppose I am interested in the even solution. Even solution means it is a symmetric solution. If you replaced x with minus x, the solution will remain the same, it will remain unchanged, right. And if you look at the functions that you have here, cos kx and sin kx, you know that cos kx is an even function, while sin kx is an odd function. So, if I am looking at even solutions, what is going to happen? I am going to have only cos kx, I will not have sin kx, and if I am looking only at odd solutions, then I will have only the sin function, I am not going to have the cos function, and that is an enormous simplification. Okay. So, let me imagine that I am going to look only at the even solutions of this Schrodinger equation. At the moment, later on I will have to look at the odd solutions. or I should say symmetric. What this means is that if you replaced x with minus x, the solution remains unchanged. And if that is to happen, what is the condition? The condition is that the function should contain only b1 cos kx, it should not contain b2 sin kx. So that actually implies that b2 which was occurring there must be equal to 0, right. So now we have the next problem. You see, we have to determine C1, B1 and the constant there is actually A1. So we have to determine these three constants A1, B1 and C1. How do I determine them? Well, let me tell you the way in which I will determine them. See, you look at the potential actually at this point it has a finite step. Its value as you cross this point, the value of the potential changes by a finite amount. So, strictly speaking the potential is discontinuous at this point, at the point x is equal to minus a, the potential is discontinuous. So, if you look at the Schrodinger equation, what does the Schrodinger equation say? In general, it says that minus h cross square by 2m. Here I am telling you something that is very general. This is the Schrodinger equation, and you can rearrange this and say, okay, this means that d square psi by dx square is equal to how much? You just rearrange, you are going to say, okay, it is going to be 2m by h cross square v minus e into psi. Is that okay? Right. If I rearrange this, I will, yeah, this is okay. Now, if you look at this equation, I mean you can say, okay, after all what is this? It tells me how much the second derivative of the wave function is, that is all that it does. And if you had a situation where the potential is discontinuous, that means the second derivative of the function is discontinuous, that is all that it means. See, if v is discontinuous, that means the second derivative of the function is discontinuous, that is all that it means. But if the second derivative is discontinuous, all that it means is that the first derivative, okay, will be continuous. And if the first derivative is continuous, what will happen? The wave function will also be continuous. So, therefore, by looking at the Schrodinger equation itself, I can say that, okay, even if I had a discontinuity in the potential, right, if the potential changes, even if the potential changes discontinuously, what will happen to the wave function? The wave function will not change discontinuously. Like this argument can be made rigorous and mathematical. Okay. So, therefore, the conclusion is that even if you had a discontinuity in V, the wave function will not change discontinuously. Its second derivative will change discontinuously, but that means the first derivative will be continuous and the wave function itself will be continuous. So, therefore, what happens is that at this point at x is equal to minus a, you have a discontinuity in the potential, but that does not mean that the wave function is discontinuous. The derivative of the wave function as well as the wave function itself is continuous at this point. So, what does that mean? It means that if I evaluated the wave function at this point using this formula, right, this is the wave function that is appropriate for this region. So, even at this point it is valid and I can evaluate its value at that point using this formula. I can also evaluate the value of the wave function at this point using that formula, and if the function is continuous, what should happen? The answer that I evaluate using this must be equal to the answer that I get using this, otherwise the function will not be continuous. So, therefore, what is the thing that I am going to have? In here I will put x is equal to minus a. So, the answer will be C1 e to the power of minus kappa a, right. That is the value of the wave function at minus a, evaluated using this expression. And what is the value of the wave function at this point evaluated using that expression? It will be equal to B1 cos minus Ka, and the two have to be equal, right. And so, what happens? You get this equal to that. See, why do I do that? The answer is actually extremely simple. I want to find out relationships between C1 and B1. How do I do that? I have to impose the condition that the wave function and its derivative are both continuous. Okay, that is the way in which I will determine the constants C1 and B1. Not only the wave function, its derivative also should be continuous, right. So, how will you calculate the derivative? Well, the derivative of this function with respect to x will be C1 kappa e to the power of kappa x, that will be the derivative, and the derivative of this function will be what? It is going to be B1 derivative of cosine kx. What is the derivative? Answer is k sin kappa x with a negative sign, that is the derivative. So, the derivative of the first function is so much, the derivative of the second function is so much, and at the boundaries you see these two have to be equal. So, if you put x is equal to minus a, at x is equal to minus a, this and that have to be equal. So, let us put x is equal to minus a, and what is the answer that you get? You get C1 kappa e to the power of minus kappa a is equal to minus B1 k sin minus Ka. So, you see that we have obtained two equations, one by saying that the wave function is continuous and the other one by saying that the derivative of the wave function has to be continuous. So, what are the two equations? Let me write them neatly somewhere. The first equation says C1 e to the power of minus kappa a must be equal to B1 cos Ka. Well, cos of minus Ka, but as far as cosine is concerned, this minus sign is not important because cosine function is an even function. So, therefore, this is actually equal to B1 cos Ka. What about the second equation? The second equation is written here. And how does it read? It says that C1 kappa e to the power of minus kappa a is equal to minus B1 k sin minus Ka, but sine function, as you know, is an odd function. So, this negative sign you can take it outside and cancel this negative sign which already exists, and therefore, this is going to be B1 k sin Ka. See, these are the two equations that we arrived at, and of course, these two equations contain the unknown quantities B1 and C1, but it is very easy to get rid of these unknown quantities B1 and C1. The way to get rid of them is simple. What you do is you take the second equation, divide it by the first equation. That means, you see, the left hand side of the second equation I shall divide by the left hand side of the first equation. What is the result? The result is actually kappa, and the right hand side of the second equation I will divide by the right hand side of the first equation. The answer is going to be K tan Ka, and this is a somewhat complicated equation which we have to solve to find the allowed energy levels of the system. This is the equation. This ensures that both the wave function and its derivatives actually are continuous. But you look at the expression, see kappa, where is our expression for kappa? I think I have probably removed it, but I should have kept it. Kappa was defined to be something and K was defined to be something else. Kappa was defined to be 2m epsilon divided by h cross square with a square root, or kappa square was defined to be 2m e epsilon by h cross square, right. This was our definition, while k square was defined to be 2m divided by h cross square V0 minus epsilon. This was the definition of k square. So, the point is that kappa and k are actually dependent on epsilon, right. They are both dependent on epsilon, and this is an equation that is to be satisfied. You see, you have epsilon inside this kappa, you also have epsilon inside that k, right. And if you are able to solve this equation, see, this is an equation that has to be obeyed. If you are to get an acceptable solution, then this equation has to be obeyed, and it is clear that this will not be satisfied for any arbitrary value of epsilon. There are only certain values of epsilon which will satisfy that condition. What does that mean? In terms of our earlier discussion, this means that it is not possible for the particle within this potential well to have any energy. The energies that it can have are fixed, they are discrete, or as we say, they are quantized, right. So, the energies are such that they will satisfy this equation, but unfortunately this equation is a rather complicated looking equation, and it seems very difficult to solve this equation. If you solve this equation, then you will be able to find the values of epsilon, which will give you the allowed energy levels for the particle. In fact, what one can adopt is a graphical solution of this equation. I will tell you how this equation may be solved graphically, and you can get very interesting results. But before I close, let me just tell you what actually is the final result. The final result is that it is not possible for the particle within this potential well to have any energy. There are only certain allowed energy levels that it can have, and maybe I can represent these allowed energy levels in this same picture. This is what we will discuss in the next lecture. So, it will have maybe one energy level there, another energy level maybe somewhere here, and a third energy level may be very close to the very close to 0, maybe something like that. It would have 3 energy levels, or maybe 4. I mean, the allowed number of allowed energy levels in the box is actually finite. Only a given number of allowed energy levels are there. So, the system may remain in any one of these 3, and if the system remains there, then what happens is that we say the system is bound, it is trapped in the potential well. Okay. And then you can also ask what will happen if the energy of the particle is greater than 0, Then just as in classical mechanics, the particle has an energy which is above 0, what happens is that it is not bound here, but it can go away. So therefore that will represent an unbound state of the particle, while these three will represent the bound state of the particle. Okay, I think we will stop here. Thank you for your attention.